to the TAMIDS seminar.
Yeah.
Today we're very happy to have Rob Nowak from the University of Wisconsin-Madison. Rob has done a lot of important work on breast sensing, signal processing, and recently neural networks. So today he's going to talk about a deeper understanding of deep learning, functional analysis for neural networks. Thank you very much.
Okay, thanks, Jonathan. Thanks everybody for hosting me today. Rice University, that was about 20 years ago, and that was probably around the last time I visited Texas A&M too. So things have changed a lot in the last 20 years, but Ron's still here. Or you weren't even there, Ron. You weren't even there then. I knew Ron. He would visit us. Okay, good. So I just wanted to say, I don't know how to get rid of that. Oh, yeah, here it is. Okay, I just wanted to, so I'm going to talk about neural networks, and I was just going to give you a little bit of my own history with neural networks. The first sort of big revolution in neural networks was prompted by this famous paper by Rummel, Hinton, and Williams about the backpropagation algorithm. That was in 1986, and in the late 80s, I was a beginning graduate student at the University of Wisconsin. And they invited Rummel to give a talk, and I thought, well, this is really interesting, but I really liked math, so I wanted to kind of say, is there anything interesting we could understand about neural networks? So I started exploring them a little bit myself. I worked at GE Medical Systems, and just sort of get my feet wet with neural networks, I tried to apply them for a particular problem in medical imaging. And I got some fantastic results out of the neural network, and I had this wonderful mentor advisor at GE Medical Systems at the time. Her name was Ann Hall. And I showed her the results. She said, "That's fantastic, Rob, but why do they work?" And I thought, well, wait a second. Nobody ever asked me that kind of question before. Why do they work? And I said, I have no idea. No good idea, right? And so that kind of prompted me. So I went back to school, and then I said, well, I'm going to do my master's thesis on neural networks, but I'm going to, again, try to study them and how they perform in a domain that I understood very well, which was edge detection images. So I wrote a master's thesis on that. I got a little more insight, but not much. And I kind of started moving away from neural around that time, because things like wavelets and all sorts of other really cool, more printable mathematical things were coming along that I was very interested in. So I moved on to wavelets and so forth. Machine learning moved away from neural networks to things like kernel methods and so forth. But of course, neural networks have come back today. But just to give you an idea of how long ago this was, this is a picture of my brother and I back then. We loved neural networks back then. We also loved heavy metal. And I still love heavy metal, and I still love neural networks. Okay, so here we are today. We just had this big announcement from Biden, and down here you can see, that goal is to develop things that allow us to determine whether AI systems are safe, secure, and trustworthy. And of course, to do this, we can do it through a lot of experimentation and testing, but probably along the way, we're going to need a little bit better mathematical understanding of neural networks too. And so that's where hopefully we all come in. So these are modern neural network architectures: the convolutional neural network, the transformer model that underlies things like large language models. Doesn't matter too much for this talk to understand what all these different blocks are doing. The important thing to know is that deep neural networks are highly nonlinear and massively parallelized functions, or parameterized rather, so not parallelized, parameterized. So they're just functions that we somehow parameterize with a bunch of weights and other things in these various architectures. And so we want to think of them that way, as functions, and what can we understand about those functions? The other important thing to know about all of these modern architectures is they involve a couple of very common elements throughout them. One is this so-called rectified linear unit, or ReLU. It's just taking the positive part of whatever comes into it. That's a kind of standard activation function that neural networks use all over the place in these architectures. And then also commonly, there's a form of regularization that's used called weight decay. I'll describe both of these in more detail as we go, but those two ingredients can give us a lot of insight into what's actually going on with the functions these massive architectures are representing. Okay, so to get into this, I want to first of all tell you a little bit about what it means to train a neural network. So here's what we would call a shallow neural network. They call it shallow because there's just one hidden layer of these nonlinear activations, these radial neurons, as they're called. The function is parameterized by weights, W and V. These we call the input weights, these we call the output weights. And the function looks like this then. You have your input X, it's some vector. You take the inner product between your input weight at a particular neuron, that input X, the positive part of that, and then weight it by an output vector V. And this is the rectified linear unit activation function of a neuron. Okay. Is that easy to understand? That's what a shallow neural network function looks like. And to train these functions, people would use an optimization like this. They would have a data fitting term. Here I'm showing you the sum of squared errors. So these are sort of your target outputs, Y's that you'd like the function to achieve at a given set of input and output pairs. You have xi, yi pairs, inputs and outputs. You want your neural network function to match those input and output pairs. We're measuring that with squared error, but you could use another loss function if you like. And then this kind of regularization is added to the training. This is the sum of squared weights. And this regularization is what gives rise to this weight decay idea. Let me just show you how that works. So if we look at this overall function, we're minimizing over the input and output weights, the V's and the W's. If I just look, for example, at one of the output weights, a gradient descent step would be the new V is the old V minus a step in the negative gradient direction. And that negative gradient is the gradient of the loss function, that guy there, and the gradient with respect to this regularizer, which is just proportional to that output weight. And so we can kind of break that into two terms, the loss term and this other term. And the thing I'm showing in red, that's this idea of weight decay. You're just taking a step in the gradient direction, and then you make it a little bit smaller by removing something proportional to the weight vector itself. So they call that, that's where the name weight decay comes from. Good? Okay. So this is the standard approach to training neural networks, possibly using different loss functions, not sum of squared errors, but could be other things too. Okay, so one of the really interesting properties that kind of ends up giving us a lot of insight to what's going on with these functions is something we call neural balance. So what do I mean by that? So if you look at this, a single neuron's contribution to the overall function, I have my input and output weights, and they kind of interact in this bilinear fashion in the sense that if I scale the input weight by some positive value alpha and scale the output weight by 1 over alpha, I don't change the function at all. This is the same function, it's invariant to this moving scale between the input and output weights. And because of that, at a global minimum of this objective we were just looking at a moment ago, at a global minimum, the norms of the input and output weights have to be equalized. And so this is what we call neural balance, just to give it a nice name. It's a very easy kind of proof. First of all, the data fitting term is invariant to this scaling because the function itself is invariant. So the only thing that this scaling affects is the regularization term. And if you just think a little bit and look at where would that regularization term be minimized, there's a certain choice of alpha. And with that certain choice of alpha, you get this balancing condition. Okay. And so what that means is that at a global minimum, we have the input and output weight norm balanced. And so because of that balancing, this term that was contributed by a certain neuron to the regularization at a global minimum is actually just equal to the product of the norm of the input weight and the output. So what does that do for us? And this is something that actually people noticed for a while. I'm putting one of the earlier references there. And I share these slides, but I'm happy to people come back and look at those. So what do we have? So we have our original optimization objective, which led to this gradient descent and weight decay idea. That's equivalent to this regularization. So these are two different functions, but they share global minima. They have the same global minima because at a global minimum of this one, I have this balancing condition. So I could have tried to minimize this objective function. I get the same set of solutions. And this is sometimes called the path norm of the neural network. And then we could do one more thing if we wanted to. We could, because again, it doesn't matter how I scale the input and output weight, I can move that scale back and forth. I could just normalize the input weights to have unit norm. And then I'm left with just minimizing the sum of the norms of the output weights. And this, and I don't know if I can move that down there. At any rate, what it says down here is this kind of regularization term is something people call the multitask lasso regularizer. It's kind of like a generalization of L1. It's like an L1 norm, except we have a sum of two norms. So we're doing some stuff.
Actually,
Yeah.
Are these three kind of formulations give the same result?
Yeah, they all have the same global minimizers.
Okay, great, thank you.
Well, you have to be a little bit more careful. If I get a minimizer of this one, of course, well, that looks so maybe better. If I get it, well, just leave it. It's fine. It'll be okay. I'll just see if there's anything cribbed down there. So at a global minimizer of this one, of course, these weights are going to be unit norm. And I told you already that a global minimizer of this weight, these two weights have to be balanced. So what you would have to do to take a minimizer of this one is just go back and rebalance, and then it'll become a minimizer. So they're basically all equivalent. Does that make sense?
Okay,
Yeah.
thank you.
So I can solve either, any one of these three, and I get the same set of solutions. Okay, good. Any other question before I move on from this? Okay, so let me just show you. So I said the title of that slide was Secret Sparsity of Weight Decay. Let me explain what I mean by that. So already, if you see something like an L1 norm regularization, you should think you're going to get sparse kinds of solutions, and you do here. Just going to try to move this. Oh, there it is. Okay, so here I'm just showing you some data points. Those are those dark spots, those little dots, and then I'm going to train a neural network with 320 neurons to fit these 32 data points. So the only thing to understand about that is that we only have 32 data fitting constraints, but I'm giving myself way more parameters than I would need to perfectly fit those data. That's kind of a standard thing that we see when people are using neural networks. And what happens if you train a neural network to fit those data points with a little bit of weight decay? So you're saying, try to fit the data, but also try to make this sum of squared weights be not too large. What happens is you see this. So the green here, this is how many steps I take of gradient descent. So the green is basically showing you how well I'm doing on that data fitting term, that loss, and it quickly goes to zero after a relatively small number of iterations. But if I keep training, you notice here, this is the sparsity. So this is the number of non-zero weights or neurons in my neural network. I get zero training error, I still have a fairly dense neural network. But if I keep training gradient descent longer and longer and longer, it ends up giving me a solution with just 12 neurons that are non-zero. So that's kind of interesting. So it says that, like, yeah, somehow you over-parameterize, but it actually homes in on this sort of not over-parameterized model, the sparse model. And there's a way to actually get that sparse model much more quickly if you then go back and look at that third optimization, which was the multitask lasso. You can directly tackle that. So forget about the first optimization, which was the weight decay one. Go to the third one, which was this lasso type optimization. I told you they'll find the same set of solutions. So we can use that third objective and do gradient descent with soft thresholding, roughly speaking, which is a proximal gradient descent algorithm. And you get also great data fitting, but you find that sparse solution very, very quickly. So there's a way to kind of accelerate the convergence to the sort of limiting sort of model. Okay. So that's kind of maybe a useful insight for practical things. This is just a picture. I don't want to say too much about it, but this is on the MNIST data set. It's a multi-layer neural network. This is 100% of the neurons are used, and these are sparser and sparser models. So you can kind of crank up the regularization and you'll get sparser and sparser. And this is showing even with just 3% of your original neurons in your model, you still get pretty high accuracy. And the red here is this proximal gradient algorithm I just mentioned, compared to some other schemes people have just sort of proposed in more of a heuristic fashion to find sparse neural networks. So we actually find them generally better than some of these other things people have proposed in the past. So good. So I think that's all I wanted to say about training. That sort of sets the stage now for how we're going to try to understand these functions a bit better. We already see that they're sort of sparse functions in some sense. Okay. Okay, so now I'll move to the next part. Just make sure no other questions about this training idea and the different optimizations.
So,
Yeah.
so can you say why the third approximation algorithm works better?
The third, but nothing really quantitative, but one sort of intuition for why this would work better. It's really operating on kind of what would be the natural function space for these particular models, and I'll come to that in a second. So it's sort of designed really to exploit the types of functions that neural networks are very good at learning, and the others are maybe a little mismatched to that functional kind of structure. So, but that's just maybe, yeah, we'll come back to that after I talk a little bit about the functions. Okay, so now let's talk about what kinds of functions they learn. So again, here's our shallow neural network. Here's the weight decay objective. Here's that second objective that I call the path objective. I'm going to first of all look at it where we just have a single output. And so now that these are just scalars here, the output weights, and it looks like this. Okay, so you could define a space of functions. They're all the functions that map RD to R that you can build by taking finite combinations of these neurons. Okay, and we can define a norm on those by this path norm definition. So this is what I call the path norm before. It turns out you can easily check. It is a norm on this space of functions. So it's a valid norm. It satisfies all the conditions of the norm. So that's good. And then you can complete this space with respect to that norm. And that is a Banach space of all the functions you can generate. You might think with infinite width neural networks. And at the end of the day, what you can do is express each of these functions as an integral over neurons with respect to some finite measure nu. So this finite measure is basically playing the role of the output weights here. But it looks like this. So you notice that the input weights are normalized, so they're on the unit sphere, so they have unit norm. And then we have this measure nu that we're integrating. That's just kind of tells us what is the natural space for functions built up using neural networks of this form, where we kind of characterize their kind of norm or complexity using this path form.
The info of this or the
Yeah, you'd have to take the info over all representations of a given function, but I'm kind of just ignoring that little detail. But yes, there could be, you know. Okay. Oh, maybe I just mentioned, I don't know if it shows up down there, but this idea is kind of old, I would say. It goes, you know, definitely Andrew Beering was kind of using this way of thinking about things way back in the early 90s. Okay, so now let's,
The
yeah.
weight W here is normalized.
yeah,
Okay.
yeah, the W, because we can always normalize the W, that doesn't really change anything, right?
Okay.
Because we can move scaling from the input to output weights because the ReLU function is piecewise linear.
Okay, thank you.
So I just want to show how this norm then is related to derivatives of that. So here I'm showing a really simple function that just has 3 of these neurons in it. So one neuron turns on, another one turns on, and the third one turns on, and it looks like this little function. If I take, well, I'm just going to show, well, so what are those different slopes? The slope is, first of all, V1 times W1, then that plus V2 times W2 is the second neuron turns on, and then you have the third neuron's contribution. So they kind of add up this way. And then if you take the derivative of that function, you get a piecewise constant function, of course, and the levels of each piece are proportional to those slopes. And then if you take the derivative of that, you're just going to get some impulses of the height of the differential of each of these steps. And so, roughly speaking, now you can see that the height of each of these impulses is exactly proportional to the product of those weights. And so, roughly speaking, the path norm, you can think of it as the integral of the absolute value of the second derivative. This isn't quite right, because of course these aren't in L1. Technically, this is what we call the second order total variation of f, or the total variation of the derivative of f. But I'll just denote that as TB2. But if you don't like that, you can just think of it as roughly like this integral L1 norm of the second derivative. Okay. Okay, so that's interesting and helpful. Kind of gives us a way to sort of think about this sort of norm that we defined in terms of weights actually has some connection back to the smoothness properties of the function. Gives us something. And so here again, I'm just kind of listing out some of these different optimizations. And so we could sort of say, well, we were optimizing this neural network over weights, or I could say, well, the neural network is a function, and what I'm really doing is regularizing the TB2 of that function. They're all the same. Okay. So BB2 is the space of all functions with finite second order 12 variation. So we'll talk about this BB2 space. And again, just think of that as the only one. Okay, so here's this first result that Rahul Pari, I should have mentioned at the beginning, this is worth quite a bit of it came out of Rahul Pari's thesis. And then a couple of my other students I mentioned, Joe and Lou, have been involved in some of the follow-up work to that. But this was the first result Rahul had. And it says that if you have, so we're going to look at this optimization over functions in BB2. So this is a variation. We're looking optimizing over function space. We have a sum of loss functions. Those could be sum of squared errors over some finite data set, xi, yi pairs again. And then we're regularizing this TB2 of the function. And what the theorem says is there's a solution to that optimization that exactly takes the form of a shallow neural network with a width k, the number of neurons, being less than the number of data points. So there's just a couple of points I want to kind of show here. So first of all, the solution has, just 1 second, has these regular neurons, and then it also has this affine term, which is what in neural network parlance they call a skip connection. We have the neurons, the skip connections, and then the overall thing is sparse. There's not a, so this is a solution, saying there are solutions that don't involve too many neurons to this infinite dimensional function space optimization. That's because we only have a finite number of data.
So in your integral description of the space of function derivatives kind of indicates that probably you deal with something like integral geometry or probably not on the unit sphere.
So here we're working over all of R.
Yeah,
This
I
is,
mean over there when you integrate over W,
Yeah.
some measures. That
oh yeah, we're there. We're
So this is kind of integral geometry problem on the sphere. It might be interesting relation.
maybe we can chat afterwards about that. So here, I just want to emphasize here we're talking about the case where we're in the univariate setting, and so these W's are on the unit sphere there. They're either +1 or -1 in this univariate case.
In the previous slide, the F did not, but here the F is minimized over the function set of bounded variations, right?
Yeah.
Now previously, there's no this kind of requirement, right? In the previous slides.
So in the previous slide, oh yeah, maybe I should have. So yeah, I guess to be kind of, how would I really think about this? Well, maybe I'd say I have like a large number of neurons here. So I'm still constraining it. So this would be over the weights, but I can still say, well, whatever those weights are, I can go back and calculate this TB2, right? It's just, that's what it is. This, for a neural network function of this form, the TB2 of the function is just this value. But now I'm kind of changing it, as you said, in this next slide, what I'm saying is, okay, let's just now not restrict ourselves. So that's important, good question. Here we're saying, we're going to optimize over all functions in BB2, not just the ones that happen to be neural networks.
Okay.
And then this representative theorem is telling us there is a solution, or that is a finite width neural network.
Okay.
So that's kind of the importance,
Okay.
because we kind of no longer restricted ourselves to stuff that we can write as a neural network, but still the solutions have that form.
Okay, thank you.
How's lambda quantified in this result? Is it the same? Does lambda equals 0? Lambda.
Yeah, sorry.
100?
I should have a little thing that says lambda greater than 0 here.
Sure.
So if I don't have that at all, then we wouldn't necessarily have this kind of representation. So we have to have a little bit of regularization, could be arbitrarily small. So should think of lambda, I should have lambda strictly larger than 0. The larger you make lambda, I don't have any kind of bounds or how to tell you, but the larger you make it, obviously, if I make it huge, the 0 function will be the
Yep.
solution.
Yeah.
And so somehow as you increase lambda, it will have more and more sparsity.
But I'm sorry, you're saying this is gonna be true for arbitrarily small positive lambda?
Yeah,
Oh, that's really interesting.
yeah.
And as lambda tends to 0, it's minimum.
It would be the function a function that has minimal TB2 that, for example, we're using the squared error for a loss would be the interpolator of the minimum TB2.
Oh, thanks.
So let me just see what else. Oh, I was gonna just start. This is actually kind of classical in a way to get this result. So the second order differential operator has Green's functions, which are things like Rayleigh's. It has a null space, which are linear functions, which accounts for that affine term there. And so any function in BB2 can be expressed in terms of finite measures. So you take your function, you take its second derivatives, that gives you a measure. And then what you can do is you can say, okay, well, we want to minimize the total variation of the measure. That's what TB2 would be in this case, subject to linear constraints, which are our data constraints. And this is basically just reduces to this classical measure recovery problem. We know the solution is a sum of impulses. And then if we apply the pseudo inverse operator to an impulse, we just get one of these radioactive equations back. So that kind of gives us this representation. Okay. So I just want to say something because I'm going to come back to this a little later in the talk. So the solutions aren't unique. So here's some data points, and here is an interpolator of those data points that has minimum TB2. Here's another interpolator that also has minimum TB2. So both of these are solutions. If I take lambda to 0, I would get these solutions. And in fact, there's an infinite number. So you can kind of do a lot of things in this region as long as the total amount of turns you take, the total number of angles sort of sums up to the two things. So generally for these problems, there's going to be an infinite number of solutions, which is a little bit something that's always bothered me, because in some sense, if I looked at these two, you said, which one do you think is a better interpolator? I would kind of like this one because it stays closer to the data points, but there's no guarantee you'll get that one when you train a neural network. So this is always been, I'll come back to that later. It's something that I worry about. Okay, so now let's kind of just say, how do you go from the univariate case to the multivariate case? So here, the function maps from RD to R. I'm just going to show you what it looks like in 2 dimensions. So here's a function over 2 dimensions. It has 7 neurons in it, so it's a piecewise linear surface. If you look down at that piecewise linear surface, now I'm just showing you that heat map looking down, and if you take this Laplacian, so you take 2 derivatives of that function, everything gets annihilated except you'll get something that you can almost think of like a line or a hyperplane version of the Dirac impulse, wherever you had one of those neurons kind of switching on or off. Okay, and now here's where this Rodon transform comes in. So the Rodon transform is going to kind of project or integrate in all these different directions. If you have to integrate right along the direction of one of these lines, you'll get a Dirac impulse. And so that's what this filtered Rodon transform does. It takes this picture, which you could think of as a bunch of Dirac lines or whatever, and converts them into impulses. And those impulses are indexed kind of by the orientation of each of these lines, and then also the offset, where it's set off from the origin. And the magnitudes of each of these guys is equal to that thing we were calling the path norm. So it kind of gives us exactly the same sort of thing we saw in the 1D case. In 1D, all we had to do is take 2 derivatives, and then we can read off the heights of these impulses, gives us sort of these path norm terms for each neuron. Here we have to do something a little more. We have to first take derivatives, then we transform into the Rodon domain. You get a similar kind of impulse picture. And so what that means is this thing I was calling the path norm is the total variation of this measure that you get after taking F, taking Laplacian, and then taking this filtered Radon transform. Okay, so we call that Radon domain second order total variation. Just another picture to make sure everybody's on the same page. Here's a two-dimensional ReLU. I'm going to take its second derivative. That gives me this thing I was calling a Dirac line. And then when I take this filtered Radon transform, I get an impulse exactly at the orientation and offset of that line. I can just kind of read off. That kind of basically reveals what was that term in your function. What was that neuron's contribution?
What was the lambda operator? Could you remind me, please?
Sorry?
What was the lambda operator?
Yeah, so that's basically,
It's filled.
it's like a high pass filter. That, if you know that, but basically it's a frequency domain operator that goes through this. Yeah, just because you're integrating, you have to kind of undo that integration. Okay. Yeah, exactly. Okay, so, right, so this picture. Okay, so now that what we ended up with then is we defined this new boundary space, we call it Radon BB2. We have this notion of Radon domain second order total variation, which is given by what I just described. I told you what the operators are. And you could kind of think of this as measuring sort of like sparsity of second derivatives, but looking at all different directions in your input domain. And then we can define the spaces, just all the functions that have the second order total variation finite. Okay. And then we have, just like we had in the univariate case, there's a representative theorem here too. It basically looks exactly the same. You end up with, there exists, again, remember the solutions won't necessarily be unique. So here, there is a representation or a solution that has this representation. Finite sum of ReLUs, the skip connections again, and the number of neurons is less than the number of data points. And so the architecture you'd end up with would be something like this. You have your ReLUs. You have this thing where you take the input, you replicate it, and it just becomes another linear term. That's what they call a skip connection. And so this is kind of a common building block in larger neural networks to have layers that look like this. And that kind of pops out of this. So again, just kind of going back to the question before, the important thing is here, I'm not restricting you to only look at functions of this type. I'm saying all functions that have finite Radon TB2, optimize over all that, over this set of finite data points, and you get these kind of sparse solutions. Okay. And the other thing that you can say about this is you say, oh, okay, well, I don't really have to solve this problem. I can just say, I already know there are solutions that only have a finite number of neurons in them. So now I'll just start off with an architecture with a finite number of neurons and use my gradient descent with weight decay. And if I can find a global minimizer of that objective, I found a solution to this variational problem. Okay, good. Let me just show you kind of like qualitatively what's going on. It's an interesting thing. So here's a two-dimensional function. It's kind of bumping up here and a little bit here, and then it's smaller away from that. So brighter colors are higher values. So it's the two-dimensional surface. We measure it at a bunch of points, and then we fit models to it. So here I'm fitting a thin plane spline. Here's a kind of kernel method inspired by neural networks. And here is an actual ReLU neural network, the ones we were talking about. They all look pretty good reconstruction of that function based on a finite number of measurements of the function values at those red sites. Here's another function. Again, I'll measure it in a few places and try to recover it. And you can kind of tinker around with some of the control parameters or regularization parameters in these two methods, but you'll never get something very nice out of it, whereas you get a kind of nice recovery from neural networks. Okay, so why is that? I'll say a little bit in a second, but basically, these two methods are linear methods. They can't adapt to this directional smoothness. Here, it's kind of perfectly smooth, or constant. In this direction, there's only variation in this direction. These methods can't sort of adapt to that intrinsic low-dimensional structure where neural networks can, and it's easy to see why, because you can kind of tune those input weights, which are essentially orienting these neurons, so they only have variation in that key direction. Yeah.
Actually, there is micro-local explanation of this.
Okay.
Since you see in the middle you have those blurring
Yeah,
It's well known in imaging in tomography that it occurs when you don't have the tangent lines to the singularity. There
okay,
is microlocal theory. You cannot touch with your line singularity wavefront. You don't feel this wavefront.
Okay, good. Well, maybe let's chat afterwards, because it'd be nice to have something besides just a picture to say, this is inevitable, right? This is me kind of playing around to try to get the best results.
Okay.
But yeah, here's a little theory that kind of explains why it is, and this is actually kind of inspired and helped along with some of Jonathan's work, but yeah, so what am I saying here? So if we have one of these functions in this Radon BB2 on some bounded domain, then we can approximate a function like that with a neural network with only M neurons in it, and we get a pretty nice approximation rate. And what you can do with that is you can kind of turn this into a result that says something like, if you measure a function f from this Radon BB2 class at endpoints, just as we were talking about before, possibly even with a little bit of noise, then you end up getting a bound that kind of involves the approximation or something due to possible noise in your measurements, and you get a kind of rate that ultimately is bounded by 1 over the square root of n. So the L2 kind of error of recovering this function from noisy samples is like 1 over the square root of n. If you use these linear methods on the same class of functions, so Radon BB2, in place one other linear methods, you're always going to get at best a rate like this, n to the minus 3 over d plus 3. So as d gets large, this is really, really slow because we cannot adapt to this kind of directional variation stuff. So this is the curse of dimensionality. And what this goes all the way back to Andrew Barron's work, you don't suffer the curse of dimensionality when you're using neural networks. So roughly speaking, these Radon BB2 spaces consist of very smooth functions, very, very smooth in all directions, or they may have some exceptions to that very, very strong smoothness, but only in certain preferred directions. So they're intrinsically kind of super smooth and or low dimensional. Yeah.
Are there any connections known between the FM that achieves this and the neural network that you get from running your penalized training method? Is there any known connection between like what you have on the computer and this thing that exists that we know of yet?
I don't know. So you're saying like if I found the best M-term approximation, say here.
Well, is that the same as what you get from just running the thing on your computer, running the algorithm that you presented at the beginning of this? Like, what's the connection between this and the algorithm that we saw in the first few slides?
Yeah, so what, yeah, that's a great question. So,
You need information about that. The question is, in what sense are you given that?
well, let me say it this way. So what does this mean right here? What is this bound? I'm telling you, it would say, okay, well, you don't get f, you get some samples of some function f that we're assuming comes from this RBV2, right? And say it has Radon TB2 less than or equal to 1. So some function from that set.
Our data came from sampling that.
And the data comes from sampling it at n random points. Let's just say it be concrete, uniformly random over that domain omega. Now you just run this gradient descent algorithm with weight decay or one of the other regular isomers I talked about. Let's say, here's the only wrinkle. I don't know that I can't guarantee you'll converge to a global minimum. You might find a local minimum, but let's say you converge to a global minimum. Then we know that that global minimum, if I plug that in and looked at its expected L2 norm, it would obey this.
Good. And since in practice, we do have at least a posteriori estimates of the error, just look at the remaining error. It might not be 0, but it might be like 0.0001. Can we quantify if FM is delta close to the global minimum, like what happens?
Yeah.
Or if the thing we get from our algorithm is delta close to that FM, what is, how does it translate? What's the logic of continuity?
I don't have a great quick answer to that, but maybe we could chat about it afterwards. I'm available. So yeah, I don't know.
That sounds interesting to me.
Yeah, because you could converge to something very far from the global minimum. Right, because it's a non-convex optimization. That's one of the problems.
When lambda is small, it is, yes, that's
Yeah.
why, that's my earlier question.
But I'm happy to chat about that more later.
Okay,
Okay,
interesting, thank you.
here's an interesting picture. Here it's the same sort of setup, except now I'm only going to measure the function at these red dots. So I don't even measure over here. I have no idea what the function looks like over there. It's not revealed at all by the samples. And of course, if you use linear methods, you sort of see something reminiscent of what was showing up, but only in those locations. It just kind of washes out as you move away. Why should it do anything else? But neural networks do something else. They sort of say, aha, whatever these things are here, I see that it's small goes up, and it can represent those samples with a small number of neurons that happen to orient themselves in that direction. So when it extrapolates off of the data, it kind of persists that pattern. That pattern persists. And so that could be good or bad, but it's very different is the point. Okay. All right, so I've got about 10 minutes or so. So I think I can wrap up the last part of the talk. So now I just want to go to deep neural networks. We talked kind of about these one-layer neural networks. How do we even start thinking about deeper neural networks? So let me kind of say a little bit about that. So first of all, we have to, because deep neural networks are going to be like multiple layers of this. So if we want to understand one layer, we have to think about, well, not just a scalar output, but a vector of outputs, because this vector of outputs will be the input to the next layer of my neural network. So we want to kind of understand these vector valued networks a little bit. So let me tell you how we think about that. So again, we have these equivalent optimizations. I'm just going to write them down. You could either try to fit the neural network to your data, and now these Ys have, say, I guess 6 outputs in my example here. So this is a 6-dimensional vector. You're trying to get your function to represent those data points. And then the sum of squared weights regularizer. And I can always reformulate that optimization this way with the L1, the constraint on the 2 norm of the W is 1, and then I just minimize the sum of the 2 norms of the output weights. And yeah, turns out this is sort of a natural norm for vector valued neural network functions. So let me explain that. Just going to follow exactly what I did in the univariate case, or the single output case, I guess I should say. So there's our optimization, and we can kind of run with the same idea. We say, okay, well, that defines a norm on the space of all functions that could be represented by neural networks of this form, possibly with an arbitrarily large number of terms in this series. And then the sort of completion of that space of functions with respect to that norm gives you something we call this kind of continuum neural network thing, where again, we have our input weights on the unit sphere, we have neurons integrating against a vector value measure in this case. So instead of a scalar measure, it's a vector value measure. And what that is then is it's, we say then the norm of a function of this type is the total variation of the 2 norm of that measure. And if this function actually happened to be a finite neural network of that form, it's just the sum of the 2 norms of the output weights. Okay. So there's a way to define a variation space. This way we call it vector value variation space. Okay. So this, again, this is all equivalent to what people are doing in practice. They're training a neural network with weight decay, but what weight decay is really doing is encouraging a small functional norm of this sort. So what does that small functional norm do? It's a little less clear to interpret than in the single output case, but I'll say a bit more about that in a second. But let me just talk about the deep representative theorem. So you can define a function space that is, I'll call it RBV2 deep, which is basically functions generated by taking compositions of functions of the type we were just talking about, these vector valued neural network functions. And then we have a kind of a representative theorem that's very similar. You optimize over this function space defined by those compositions, and it has solutions that are sparse multi-layer neural networks. So multi-layer neural networks just happen to be optimizing this sort of variational problem. Again, means we can solve these problems in this function space by just training neural networks with weight decay. Okay, so now let me say a little bit about the effect of weight decay. What is it doing? This is kind of some interesting things come out of this that maybe have practical significance. So here again is what weight decay is doing to the function. It's trying to make this norm, this variation norm, small. So think about a neural network, a single layer of a neural network that looks like this. If each of those edges is a weight in my neural network, if they're all sort of like proportional to a constant, I'd say, then if you calculate this norm, you get a value that's proportional to the width of the number of neurons times the square root of the output dimension. If you sort of say, well, what about another neural network that happen to have still weights that were like constants, but I only have kind of sparse connections in my neural network, kind of like some constant number of connections between every input and output here, then the norm grows like d, the output dimension. And then finally, if we go to another form of sparsity, if I sort of say, well, again, each input and output only connects to a small number of neurons, but those connections share. There's 2 neurons that are involved here, then the norm is even smaller. So the number of edges in these two is exactly the same, but this norm is much smaller, square root of d instead of d. So somehow what I'm trying to say is that this norm is trying to get you to find neural networks that look like this. They have sparsity, but sparsity in the sense of just selecting individual neurons. Okay, so here's a really kind of interesting consequence of this that I just kind of thought of a few days ago. So what I'm going to say is, now imagine I have one of these neural networks, I have 2 outputs, and one output is the red points, and the other output I'm trying to fit to the blue points. So I have 2 outputs, 2 data sets, same x's, so same set of x's. These are the x locations, right? But the y locations are either the blue or the red. Okay. Does everybody understand the setup here? So we talked about the red before. The red, there were multiple minimum TB2 interpolations of the red data. Here are 2 of them. There were an infinite number. In this particular case, I picked the blue data in a particular way, so there's only a unique minimum TB2 interpolator of the blue data. So now you can say, well, what happens if we train a neural network to fit both of them simultaneously? And something kind of interesting happens. Because of this neuron sharing property or encouragement that I just showed, there's a unique solution in this case. So you'll actually get this guy and this guy. You'll never take this one or any of the other solutions to that red interpolation problem. Sorry. Yeah, so that's kind of an interesting thing. Like somehow just adding an additional input eliminates some of the ambiguity in what the solution could be. So more outputs kind of constrain things more, which does make some sense. Let me just kind of wrap up. I just have one more observation to make. So another thing you can do with this is actually get better understanding of how wide neural networks really have to be. So let me just kind of give you the setup here. It's pretty simple. But imagine we're looking at a particular layer within some deep neural network architecture. So I have some training patterns coming through my neural network. They come into this layer eventually, after they've gone through maybe multiple other layers before they got there. And they're going to have these input weights. And then what's going to happen first is you can imagine there's some vector of outputs. For each input pattern, there's a vector of outputs coming out of the neurons, and they call these phi guys. And then I'll apply my output weights to those guys, and I'll get outputs from that whole layer. I'll call that psi. So I have phi is just what's coming right out of the neurons before I apply these weights, and then the psi's are what happens to each pattern after applying the weights. And so with a little work, and this is kind of a Carthy-Adori type of reasoning that I could go into later if people are interested, but if you look at these 2 matrices, and you then say, well, how many neurons do I need here? It kind of depends on the ranks of these matrices. So the number of, there exists a solution with k neurons where k is less than the product of the ranks. And that product of the ranks is always less than n the number of total training patterns and d the output dimension of this layer. And the reason that's kind of interesting is that prior to this, there was some other bound that somebody came up with that said it was bounded by the square of the number of input patterns. But already we see that as long as the output dimension is less than the number of training patterns, you would have an even sparser solution. And I'll just kind of explain, so it's relevant in practice because when people train neural networks, they see that layers become very low rank. So here's just an example of that. So this is a very deep convolutional neural network trained to minimize some loss on what's called the CFAR10 data set of images. We're trying to do image classification. There's a final layer in this neural network that looks exactly like one of the layers we were just studying. It has 512 neurons in it. So that's just the architecture that people use. It's just they say 512 is what we're going to use, and it has an output dimension of 10, one for each class here. There are 10 different classes of images. And so the theory says that we can go in and check what is the rank of these matrices. In this case, the rank is about just 10. This one, this is only 10 dimensional, so that's 10. But it turns out this is also that what's coming out of this layer of neurons is also only about rank 10. And so it would tell us the theory that I just showed you says you really don't need 512 neurons. You probably only need more like 100. And what you can do then is you can take that, what I call multitask lasso optimization, apply it to the pre-trained neural network and just see if you can find a sparser representation of the very same layer. So what we're doing here is we're actually finding an equivalent neural network. It's exactly equivalent, has the same input-output patterns with respect to the set of training data that it was trained on. So that's this training loss is basically the same for the two, but we can find a solution that instead of having 512 neurons in that final layer, only has 47. And so that's, people like this, they like to make neural networks smaller so they can put them on your phone and so forth. So that's an attractive thing for that, but also we can even see here that we're getting good test accuracy too in the two methods. We're not losing anything, even though, so here we expect this. We've actually designed that neural network to have exactly the same behavior on the training data. So these should be about the same, but the test accuracy is also maintained, even though the functions are presumably not exactly equivalent. And we've even seen some evidence that this kind of retraining, if you will, to find sparser solutions can give you some added robustness. So let me wrap up with that then. So we have these new function spaces. I've told you a lot about them. They're Banach spaces. They have all these interesting properties of spatial and directional adaptivity to smoothness. Weight decay, which is a standard type of regularization people use, is equivalent to this multitask lasso regularization, which kind of gives you all this sort of sparsity type of stuff, and is supported by a lot of people, including some projects that we're involved, Ron and I have involved. I think it's like this one here or something. So I'll stop there and happy to take any further questions. Thank you.